Hello, everyone, and welcome to this first SpaceSense webinar. Thank you, everyone, for being there. Good morning for some of them, for some of you. Good afternoon for others. We're really happy to have you with us today. So today the webinar is going to be focused on how you can use satellite data in Agtech solution and how to make it simple. With me, first of all, to introduce myself, I'm Sami. I'm one of the co-founder and the COO of SpaceSense. And with me in the presentation, we will have Tony, our head of remote sensing at SpaceSense, as well as Sambav, machine learning engineer at SpaceSense as well. Let's get started right away. To give you an idea of how the webinar will go, we have 5 main steps. First, the objectives, where we will review the elements that we aim to go over during this webinar. Presentation of SpaceSense, just to give you an idea of who we are and what we do. And then we'll go start with the first main part, which is the challenges of satellite imagery in agriculture and how to handle them. So for some of you, this might be something that you have already heard or seen, but this is also a short reminder for the people that might be a bit less aware of what satellite imagery is and what it can do. And the main part is going to be in part 4, where we will go over 2 real-life examples. The first one on advanced agricultural input management, and a second one on crop type detection and how they were made easy by using SpaceSense. And finally, we'll close this webinar with any questions that you might have. Okay, so if we start on the webinar objective, our goal is that by the end of the session, you are able to assess what type of satellite sensor is going to be relevant for your need, that you would be able to identify and avoid the pitfalls that are commonly encountered when working with satellite imagery in agriculture, that you can understand that using satellite imagery to build more accurate solutions through multiple data sources, and finally that you are able to start building your Agtech application in just a few hours. So little guidelines as well for this webinar. You can see on the bottom right that you have a chat as well as a question tab. So if you have any questions, please ask it in the question tab, and either Tony or Sambav will answer it directly in text, or if it's a bit more complex, we'll take the time at the end of the session to answer it live. And finally, the replay of this webinar will be posted online in the coming days. So yeah, you can just follow on, don't need to take notes, and everything will be provided to you in a few days. All right, then let's get started with the first part. Who is SpaceSense? Well, SpaceSense is a company that provides a solution that makes building application with satellite imagery 80% faster and cheaper. We are a French company based in Paris. We are 15 people and we were created in 2019. Our goal as a company is to democratize the use of satellite imagery by making it easier to use and more financially accessible to companies in agriculture and environment. An important point is that SpaceSense does not build insight. You might wonder why we don't build insight. Well, we believe that you are the expert of your industry. You know it way better than we could do it. Our expertise at SpaceSense is on satellite imagery and AI. And we believe that our job is to help you and users of the data scientists in the agricultural industry to unlock solution faster. So that's why we provide tools that will enable our customers to build their own internal insights model themselves. So here below, you can see some of the examples that are currently being built on top of SpaceSense by different companies. Just to give you an idea of scale, right now we are processing more than 15 million hectares of satellite imagery each month, and we are monitoring fields in over 30 different countries for customers like the ones that you can see below. A lot of them are farm management solution or irrigation management solution as well. So now that you know a bit more what SpaceSense is, we can go into the first part, the challenges of satellite imagery in agriculture. Here we have identified 4 main challenges. The first one and the most basic one is knowing what can be done. This is by itself quite a challenge when you don't know exactly what the image is, what it can do, and especially also what it can't do, what is not realistic. The second part is finding the right sensors. There are more and more satellites going up in orbit, which is great because it means more data, but it also means that we have to understand better which sensor is adapted to our use case. Third, it's going to be on focusing on how to improve the quality of the results by using grown data. And the fourth one will be common mistakes that we have identified over our 3 years of experience with talking with Agtech companies. So let's focus on the first one, knowing what can be done. So satellite imagery is an extremely powerful and very versatile data source. That is great, but it is better suited for certain situations. And we have identified a few common traits that are often the mark of use cases which could benefit from satellite imagery. The first one is frequent information refresh. So having information on a daily to a monthly basis is obviously something that is going to be much more cost effective by using satellite imagery. The second thing is large-scale monitoring. So if you need to only monitor a few fields over a few acres or hectares, drone is probably going to be more efficient. But if you need to do the same thing at a region or global level, then yeah, satellite imagery is definitely uh, the best solution. And third, if you need to have an independent data source to assess something from an impartial standpoint, satellite imagery is obviously something very interesting. So here we can see some of the use cases where satellite imagery shines. For example, and this is something that is coming up a lot recently with carbon credits, being able to monitor farming practices remotely using satellite imagery. This is very efficient. Or monitoring regional trends, for example, being able to know in a specific region how many hectares or acres of a certain crops are being planted and what is the estimation of yield so that the logistical chain post-harvest can organize itself. And then you have use cases where satellite imagery is, at least for now, significantly less relevant. If, for example, you need to look at something at leaf level for disease detection, for example, satellite imagery today at least is not able to provide that information. Or if you need to do pest management and pest detection, this is something that can be seen from satellite imagery, but it's probably going to be too late for you to do anything on that. Uh, but for that, there are actually new sensors coming up that could in the future help us for these use cases. And this leads me to my second point, the right sensors. So historically, there have been two main type of sensors used in agriculture, and one significantly more than the other, and that is multispectral imagery. So this is the most common source of satellite imagery. It's most suited for visual monitoring, and this is where we get common vegetation indices like NDVI that are now a standard in the industry. So this type of data has been available for more than 20 years in agriculture. Then there is radar imagery. So this has grown significantly in usage over the last 3-4 years, and it helps solve one of the main issue of multispectral data, and that is cloud coverage. The advantage of this technology is that it can see through clouds and at night, and it provides also very good information on the texture of the material that the radar is capturing. So this is very interesting to track elements on soil, for example, soil texture, soil moisture, and it can also be used for height estimation as well as volume and biomass monitoring. So these are, I would say, the commercial application that we can see today in agriculture, but you have others who are coming up. So hyperspectral data. So this is multispectral, but significantly more developed, and it allows us to see a lot more in the field. It can, for example, well, at this point, it's very experimental. There is no commercial very good advanced commercial product out there yet, but it should be the case in the next year or two. And this is very efficient, for example, to detect different varieties of the same crop, or try to assess in more detail something about diseases that we cannot see with multispectral imagery. And then we have thermal imagery, which is, as the name implies, something to monitor the temperature of what is captured. And for agriculture, it is especially interesting to monitor the soil temperature, which is obviously quite related to irrigation and soil moisture. And so you have these different sensors by themselves, which provide different use cases and application. And on top of that, you then have to take into account the fact that you have different resolution and different revisit frequencies, which will obviously impact the type of satellite data that you want to take based on your use case. And this leads us to the third point, using ground data. At SpaceSense, we are quite convinced that satellite imagery by itself is not good enough to provide advanced solution for agriculture. And we're pretty sure that you share the same opinion. A real-world solution actually needs satellite imagery, but also ground information like sensor data, machinery maps, weather information, soil maps, elevation maps, all these information that actually give clear data on what's happening on the ground. And by combining these different sources, we are able to provide significantly more advanced insights. But this also means that you have to deal with additional issues like different file format, different size, different temporality. For example, how do you deal with the fact that you get one image a week with your satellite and that you get one data point every 10 minutes with your sensor, different projections. So all of these elements have to be taken into account and are quite time consuming. And the last part for this first part is common pitfalls. We see one pitfall that we see a lot is people believing that one model will work for everything. For example, a crop type model will work in every region of the world for each type of variety of crop. And especially in agriculture, this is false. It's extremely based on the type of climate and the topography that the model was trained on. So this is something to be very careful about, and always make sure that the limit scope of efficiency of the model is clearly defined, because otherwise, if you try to adapt it for another region, it's going to lose performance significantly, and it can create false information. One of the second pitfall that we see a lot is that if you are able to build and generate insight from one satellite imagery, it's going to be easy to do that for 1,000. And although generating insights is obviously an intensive R&D task and requires a lot of time, being able to scale a satellite imagery pipeline is, in my opinion, something even more complicated. Due to the volume of the data, due to the type of data, it requires a very specific expertise, and you have an advanced need for data engineers and software engineers to be able to set up such a system. And third, some of you might already know that, but we were actually surprised to see how many people still believe that indices are not the truth. They are an approximation of what's happening on the ground, and they should not be used for more than that. Yeah, they are a great way to see trends of what's happening on the field, but they should not be used directly to try to calculate yield or more advanced information on the crop. So that was a quick overview of the challenges that we have identified and the little things that we believe you should be careful about when building satellite imagery to make things easier. And now we can actually go into the second part, which is real life example. Just before that, we need to do a very short presentation of what we offer as product as SpaceSense, because it will obviously influence the presentation that we will do. First, we provide a low-code Python SDK, so a library that you can integrate into your environment in a few minutes, and this will help you on three main issues. The first one is providing you access to analysis-ready data. The idea here is that if you have 10,000 fields all over the world, and you want to have information from a certain satellite over the last 3 years, this should be 2 or 3 lines of code, and all the rest should be done very easily. The second part is data enrichment. So here, the idea is that, as I mentioned earlier, the fact that ground data is, in our opinion, very important, we want to make it easy. So here you're able to mix any sensor data, any machinery information, any soil, any maps, um, any data basically that has GPS coordinates. You should be able to mix it very easily and create a unified data cube that can then be used into your analysis, into your algorithm, and into your machine learning models. And the third part on which we provide support is on data preparation for data science. The idea here is to help the data scientist or the developer, the user, to transform the data cube from this format into something that is ready to be ingested into a machine learning model. So here it's about cleaning the data, augmenting it when it makes sense, extracting the different features, also doing the patching, all the elements that are necessary to accelerate the progress from having my data into working on my model. And you'll see that in a bit more detail with Samba's presentation a bit later. An additional point on top of this library, which is something that you can use really the way you want, we have something that we call solution template. So these are pre-written training workflow for very specific application. We have that today for crop type detection and for land use classification. We built these solutions to help companies accelerate even further the creation of specific use cases, and in this case, the two that are mentioned here. The idea is that we already define all the steps that have been done from data preparation to model definition and settings, and the only thing that is left for the user to do is to input their personal information to get a specific crop that they're interested in, or detect a specific type of land based on what they want to build. And this allows them in just a few hours to create a product that is going to be a baseline for them to start working on and create their solution. So now that we are done with the short presentation of SpaceSense, we can go into our first example. So here it's advanced agricultural input management. So to give you a little bit of context on what it is, here it's a company, an Agtech company that is providing agronomic advice for fertilizer and pesticide management. And this company wants to build a model that will help them precisely provide the time, the date, and the in-field variability for fertilizer and pesticide application. So for that, they have their own sensors, and additionally, they want to build a data set that will combine satellite imagery from Sentinel-2, weather information from ERA-5, soil maps that they get from, in this case, the US government, and elevation map that they also get from the US government. So here you can see the main steps that are necessary in the construction of such a product. You have the data preparation first, then the part where they build their model, and then once the model is satisfactory, they can deploy it. So here you can see what they have to do on their side and what SpaceSense does. So they have their own AOI. So AOI stands for area of interest and TOI for time of interest. So here they provide their field and the period at which they want to get the different data that is mentioned just above here. So once they have provided that, the library will automatically do the imagery acquisition, the pre-processing, the fusion, and make it ready for machine learning ingestion. And then the model building is something completely on their side. As we mentioned earlier, we are not the expert. This is not our job, and we want to help you get there faster. So they will do their own model selection, test their parameters, and do an iterative process until they're happy with the quality of their model. And then when it comes to model deployment, here we participate again by providing a scalable data preparation ingestion pipeline. So the process that was done in this part here is now ready to be done on the fly for each new field that they have to process every day. And then they run the model on their side and they extract the insight. So here in this case, we save about 75% of their time in terms of development and 90% of their costs compared to if they had to do it themselves. And now to actually give you a real presentation of how that looks in terms of code, I'll let Tony take over the presentation.
Yep. Yep, now sharing my screen. Thanks, Sammy. So as described, this use case is over agricultural fields, and in this example, we'll want to use the SpaceSense library to search, download, and fuse together multiple data sources, including multispectral satellite observations, weather data such as precipitation and temperature, as well as the custom user-provided files, in this case, elevation and soil type. So all of this data needs to be cleaned, harmonized, and really ready to go for the user and the next steps. So to begin using the SpaceSense library to create this data, we first start off by importing the library itself, as well as other libraries that we'll be using to process and analyze the data. We also set our API key to give us access to the SpaceSense library functionalities. From there, we then specify our area of interest, our AOI, and our time of interest, as well as initializing the SpaceSense client in one line, and then a few options can be enabled as well. In this case, we're saving the resulting fusion to a file in our local directories. In this case, for this example, we're using an area of interest that is over the United States state of Nebraska, over about a little less than 3,000 hectares of corn and soybean fields mostly. And we're going to be looking at the entirety of 2021 for our time of interest, from January to January 2022. So now all of that is set up, we move on to actually searching for the Sentinel-2 images that we're looking for. And in this case, we want really clear cloud-free images. And we do that by using the S2 search functionality, where we pass our AOI, our start and end date, and any filters that we're enabling here. In this case, we're using something called valid pixel percentage. And this is a custom filter that we use to combine all pixels that are non-cloudy, not cloud shadow, not snow or ice, and not no data. So this should really get us really high quality cloud-free images. And we set that filter to greater than or equal to 99%. So that's a very high threshold. And so the search operates, and it's important to note that this filtering that we do over clouds and snow and cloud shadow, that is performed on the AOI level. So we don't get the entire S2 tile and then perform the cloud checks. We actually get it over your exact AOI, so you get very high quality filters there. So we perform this search, and we get 49 different scenes that meet our criteria over this AOI. And it's important to note as well that this is just getting the metadata for the scenes. We don't actually go ahead and process and download the scenes just yet. So we get 49 scenes for the year, which is pretty good for cloud-free. And then we move on to weather data. We're interested in this case in precipitation and average temperature. So we perform a very similar search using the weather search functionality, passing the AOI, the start and end date, as well as the variables that we're interested in. Now, ERA5 provides daily data, but for this example, we may only want the weather data that corresponds exactly to the Sentinel-2 dates that we have found. So we can use pretty simple Python pandas data frame manipulation to match those dates up, and we get a data frame search result from the weather that corresponds exactly to the Sentinel-2 scenes that we have searched and filtered. From there, for the Sentinel-2 data itself, Sentinel-2 provides 12 spectral bands, but for our use case, we don't need all 12 of them. We only need the blue, the red, the blue, the green, and the red spectral bands, as well as the near infrared. And then we also download the scene classification band that is provided by Sentinel as well. And finally, we have two vegetation indices, common vegetation indices that SpaceSense on our end, we provide as very easy ways to access the simple calculations here. So NDVI for one of them, and one way to calculate leaf area index. Next, as described before, we need to fuse some custom information here. In this case, we have a raster file that is the elevation data provided by the shuttle mission DEM, and we can specify that by using the raster functionality, the raster object, and then specifying the file itself. And then for the soil type, we do something very similar with the USDA soil type vector that we have downloaded, and we use the vector file type to specify that information. Now, this data has multiple attributes, but we're only really interested in one, which is the soil key. So we can specify only that attribute to fuse. On our part, we can accept most rasters and most vector types. So you should be well covered in any geospatial information that you have. So from there, we have specified all the data that we want. And what's left is to actually fuse it all together. So this fusion process itself harmonizes the data and makes sure that every pixel is correctly aligned, one on top of the other. And we get, as a result, a very clean, harmonized data cube that has all the necessary data that we need to further process or further analyze or plug into our machine learning model. And this fusion itself is performed very simply in just one line here with the fuse function. And we just specify the data that we had previously assigned in just the top few lines. The results here is represented by this X-array data set. And we can see this has all the information that we had previously wanted. Here we have the 49 different time steps that we found from Sentinel-2. And we see all of the data variables that we specified, all of the Sentinel-2 variables from band 2, 3, 4, 8, SCL, and the vegetation indices. And we also have the weather variables of precipitation and average temperature. And then finally, on the bottom two layers, we have the digital elevation model that we specified as a raster, and then the rasterized version of the soil type vector provided by the USDA. Also important to note, because we enabled the local output option, this X-array dataset was saved to our local machine as a netcdf. Also included in this fused object is all of the metadata and all the geospatial information that you'll need, including CRS transformations, the data lineage for all of the data that we provide for Sentinel-2 for weather. You can see exactly where this information came from, if any processing steps were applied to it, what processing steps and how. And you can even see in some of the Sentinel information, you can see the band wavelength for each individual band, as well as all of the scene titles that we fused. So this is really just to enable you to reproduce the information if necessary. So now that we have the actual fusion result, we want to kind of visualize it and analyze it a little bit. We can do that by calling a few included functionalities like plot time series, where we specify a single variable. And here we just look at the NDVI curve over the entire year, and we see a nice healthy vegetation curve over the entire year, and also shows that we did get cloud-free data. We can do the same thing with variables of weather, the precipitation and average temperature, and we can see very normal things, some storms on the observed days of Sentinel-2, and a nice temperature curve that corresponds well with what we would expect in Nebraska. Next, we can actually go through and visualize some of the stacked images. What we got in the fused dataset were multispectral images of each individual band. So we got the red, the green, and the blue bands, but we also want to combine them sometimes and view them as the human eye would. So we can do that by plotting the RGB function. And we specify one date here just to see, yeah, this is our AOI. This is some healthy corn and soybeans. Also irrigated by the looks of it. And then we can, if we want to look at all of the data, all 49 time steps, we can do just that. And we see a nice transition from very early winter with some snow oftentimes to spring, where we see the vegetation cropping up, eventually into summer with some nice dark green, healthy vegetation. And then finally, it goes into senescence and harvest. So this is just a good example of a nice way to visualize the time series and visualize the RGB for all of these days. And this was just one way that we can visualize it using the included functions with SpaceSense. But this is an X-array data set. You can use it different Python libraries to visualize it as well. And just to prove that, we have this little loop to plot each individual layer in the data set using matplotlib. And we can see the individual bands of 2, 3, and 4, the near infrared band, band 8, scene classification, S2 here, and the 2 vegetation indices, NDVI and LAI. And then finally, we also see the 2 custom data sets that were provided as the DEM and the soil type. So yeah, this is just one example over one AOI over 1 year, but at the same time, we can also scale this up. There are a few ways to do this. We can scale it up by using the same functionality that I just showed to you in this mode and just do it over a loop over multiple AOIs. But for more complex and heavier use cases, we also have a batching option available that will really speed up that process. So now that all of that is explained, I hope this basic example of using the SpaceSense library demonstrates the ease of obtaining satellite information and weather data and fusing it with other geospatial data. So with that, I think I'll hand it back off to Sammy. Thank you.
Thank you very much, Tony. If any of you have any question on that presentation, please feel free to ask them in the question panel. And we're going to go directly into our second example. So here it's about creating a custom crop type detection solution. So here our company profile is an Agtech company that provides carbon credits to farmer and then resells that to larger companies interested in buying these credits. So here, the goal of the company is to build a custom crop type detection model for Western Europe to monitor carbon credit practices at a large scale. And for information, they tried several off-the-shelf solutions that provide maps of crop type, but the accuracy was not satisfactory, which pushed them to try to build their own. So here they're going to use the crop type solution template to build their model. So let's look again at the 3 steps in the process. So we have here the data that they will be providing is historical field information that they gathered over the last few years from their farmers. They have more than 10,000 fields for which they have the crop as well as the harvest date and the sowing date, which is going to be used as the training data here. So they add that in the field selection, and then just like we did for the previous example, SpaceSense is going to do the imagery acquisition, pre-processing, ML ingestion. The main difference here is that we are going to also work on the model building. We are going to provide a model as well as parameters that we know are performing rather well for this use case. Obviously, the user will be able to tinker it, adapt it to make it more suited for the use case and increase the performances. And once that's done for the model deployment, it's pretty similar to the previous use case as well. We provide a scalable data preparation ingestion pipeline, and then they can run the model and extract the insight. So here again, we try to save a significant amount of time and amount of spending for the creation of these products. And for the real code application, I'm going to leave it to Sambhav.
Thank you, Sammy, and hello, everyone. I hope everyone's having a nice day. And yeah, as Sammy mentioned, the idea behind solution templates is that we give you an initial version of the pipeline, which helps you get to your final product faster. And here we'll be taking a look at crop type segmentation solution template. So let's get to it. Actually, 2 things before we start. The first thing to note here is that we're using a toy sample dataset, so please keep that in mind when looking at the plots and the figures and the results. And the second thing is that the code that is visible in this notebook is not all, where we've implemented many custom modules that are actually being used here. Okay, so with that said, let's get to it. The first part is just the library imports and initializations. We import all of the libraries that are needed, as well as initialize our SpaceSense library, right? Then we move on to input data. And you as a user, this is the part that you'll mainly be interacting with. You put your input data here in a data mapping dictionary where you specify your field boundaries in the form of geojSONs, and it's mapped to the vector crop masks in the form of a geo package or a shapefile or any other file. So the idea is that you put your input data, and the pipeline after this should run and give you a machine learning model. And let's see how that's done. You also specify the start and end dates regarding the sowing and the harvest dates, corresponding to the sowing and harvest dates, sorry. So now that we have our input data, what we want to do is for each AOI, we want to go and we want to download the fused S2 and vector data. So we've implemented a function which is built on top of the SpaceSense client library. And what this function does is, first of all, it will query for S2 data. It will select the best date, the one with the least clouds and the best data quality, and it will download that data. You can also specify the bands that need to be downloaded as a parameter to the function, and as well as where to save this data. After the S2 data is identified, we pass this to the fusion object that Tony showed you in the previous presentation, and we pass the shapefile or the geo package, right? And the SpaceSense client library, it runs data fusion and gives us a fused S2 and vector data file. So now we have these files, but the next step that we want to do is we want to transform them into a ML-ready dataset. Now, you might ask, why do we want to convert to an ML-ready dataset? Why can't we just train on the images that have been downloaded? And the reason for that is that a lot of the times the AOIs or areas of interest, they're pretty big. So the files that you get from Fusion, they might be of the size of, let's say, 3,000 by 3,000 or 7,000 by 7,000, right? We can't feed that to a machine learning model. We want something a bit smaller. So you want to split these images up. And when you're splitting these images up into smaller images of, let's say, 64 by 64, 128 by 128, you also want to check the data quality of each of the splits again, right? Because they're being passed as individual images. So that's what this next function does. It creates splits, and the function takes parameters with regards to the split size and the data quality, as well as where to save it. So yeah, first of all, it creates the splits. It then saves them in multispectral format as multispectral data for the in the form of netCDFs, as well as RGB format in the form of PNGs. So you can use whichever is more appropriate to your use case. It also saves a Cocoa annotation file, and the Cocoa annotation file is just an annotation format introduced by Microsoft, where it's helpful because it stores all of the segmentation masks in an encoded format into a single file, and you can very easily filter through them using category IDs, image IDs, etc. Yeah, so that's what this function does. And I forgot to mention, but it also performs the data quality checks and discards invalid images according to the limits that have been set. Just for visualization purposes, this the RGB image is the image from our AOI. It's pretty big, right? And the red grid that you see is the splits that we've created out of them of size 64 by 64. It's also necessary to mention that for the visualization, we're showing RGB, but the splitting function and everything else, it'll work with if you add any other Sentinel-2 bands as well. Next, we can move on to visualizing the dataset now that it has been created, right? So we first visualize the information data frame, and here each row corresponds to a single split that has been generated. It contains the metadata with regards to the data quality, as well as some metadata with regards to the class distribution in terms of the class value count for each of the classes. This is helpful when we're performing an EDA, which stands for exploratory data analysis, to just see what the class distribution is in our data set and how we might want to do train test split validations and understanding the data set in general. The next thing is the Cocoa annotations for the segmentation marks. So as I mentioned, it's a single file, and this is stored as a JSON, and it has the following headers. It has the images header, categories, and annotations. Then we visualize the images from the data set, and you can see in the first row it's the S2 images, as well, and in the second row it's the corresponding ground truth mask for the same. Now that we visualize the data set, let's move on to looking at two of the plots for class distribution. The first one is the instances per class for each of the classes. Right. So what this plot is trying to show us is a certain class, how many times does it occur in my data set? And the other plot is the pixel count. So this shows us how many pixels does it have in the overall data set. We can use these two plots to draw some inferences with regards to the class imbalance, the class distribution, as well as seeing some inferences such as for footpaths. We see that it has the third highest pixel count with the highest instances per class. So what we can sort of infer from this is that the segmentation mask of it would correspond to thinner lines or a few pixels per image, right? Because it has lots of instances, but not the highest pixel count. So yeah. These can also be used when you're creating your train test validation splits, because you want to have equal distributions of these parameters across all three of your splits. Now that we've looked at our data set briefly, let's train a machine learning model with it. Right. So we'll be training a unit for segmentation. And the first thing that we need to do is we need to define a data loader. So the data loader, what it does is it just loads your data set. It'll load batches of 4 or 8 images or anything that you specify, and it will feed that continuously to the machine learning model. You can also customize your data loader a little bit with regards to passing the image IDs, image size, if you want to resize them, as well as category IDs. And then we define the loss metrics for our data set. So loss is just a way for the machine learning model to compare the ground truth and the predictions that it generates. And it tells us how good the model is doing, and it helps the model in optimizing. Next, we create a machine learning model, and this is done by using the segmentation models library. It's an open source library built on top of TensorFlow, and we use it to create a unit. It allows us to very quickly prototype segmentation models. And here we're using an efficient net backbone as well as some other parameters that have been mentioned. Next, we train the model. And then we can move on to visualizing some of the stats and the predictions that have been made. Right. So one of the metrics that we'll take a look at is class-wise IOU. So IOU stands for intersection over union. So what IOU tries to do is it tries to measure, it tries to see how good the segmentation masks are for each class. And it ranges between 0 and 1. And the higher the value of IOU, the better it's doing for that particular class. We can also take a look at some of the visualizations from that are generated by the model. Do keep in mind that it is a very small toy data set, but the predictions that are being generated are still pretty decent. Yeah, and basically with that, after running the whole pipeline, you have a machine learning model that is trained from scratch with your custom data. And as I mentioned at the start, there are a couple of there are custom modules that we've implemented. There are decisions that we've taken with regards to the data preparation and the quality checks there, as well as some of the decisions with regards to the model training. Right. So if you want to discuss this as a user, please feel free to reach out to us, and we'll be more than happy to discuss. And with that, I'll hand it back over to Sami. Thank you.
Thank you very much, Sambhav. And that actually concludes the main part of our presentation. Before we go to the question, just to let you know, obviously, if you are interested in having a look at the solution or having a trial, we do offer a free option. We are also, we would be very happy to have a discussion with you. If you have a use case that you want to have a more detailed look at, please feel free to reach out. My email is right here. And now we can go to the question part. We already had some questions that were asked. Please feel free to add them in the question panel. Maybe to add something on the answer for Guillaume, which was asking how we produce our LAI index. Indeed, we have in our documentation the formula that is being used to generate that LAI index, but that's just one way to calculate it. And you can obviously, with our solution, use the raw bands, and based on that, in a couple of lines of code, generate new indices based on your needs with your personal formula, so that it can fit your needs.
Yep.
So yes, please don't hesitate to ask any questions that you might have.
And I guess in the meantime, I can reiterate some of the questions that were answered in the chat as well. The first one was about the monitoring depth for thermal and radar observations. And while this can depend on the soil type, the soil moisture, and especially the band wavelength for radar, for both of them, we can approximately say that it's the first few centimeters of soil that the radar and the thermal bands really get the observations from, which is a very good question. And that's an important information to know when you're talking about soil moisture. If you're getting satellite radar data, you're not going to get total root zone soil moisture. You're just going to get the surface level, which is still a very important observation, but you're just not going to get the entire column.
And yeah, the second question was from Stephen on asking if we do have our own machine learning platform on our side. Yeah, at this point, we do not provide the machine learning platform. A lot of our customers already have their own solution for that. So we provide them a way to easily integrate the data preparation part, which we provide through a library, and directly ingest that into their machine learning training platform. It is something that we aim to do in the future, but at the moment it is not available on the platform. Okay, and it looks like there is no more question at this point.
I think Sanket is typing something in chat as a question, so yeah, we can just
okay.
wait out for that.
In that case, yes, let's wait for the question. Yes, so the question, our target customer, the business model is in the one-time purchase or subscription model. So our main targets in terms of customers, or empirically the people who are the most interested in our product today, are companies who are interested in using satellite imagery to create new digital products that have different sources of information. As you've seen, the data fusion is a core part of our product, and it definitely saves a lot of time for these companies. One of important thing is that most companies are not focused on satellite imagery. It's not their core business. It is a way for them to generate their insights, but it's not their core expertise. When it comes for the business model, we do have a subscription model, which gives you access to a certain amount of credit based on the subscription that you take, and then you can use these credits completely freely for all of our function. If you want to download several millions of hectares of Sentinel-2 for 500 credits, you can use them that. Or if you want to split it between Sentinel-2 and Sentinel-1, or then if you want to input your own data and fuse it together, all of these different features have a unit price that you can use completely freely. Okay. No problem. It is my pleasure. And in that case, if there is no more question, we'll stop the webinar here. Thank you very much for attending. We hope it was interesting for you. Please let us know. We'll reach out to you anyway for some feedback, as well as the video of the webinar if you want to have a look at it further in the future. So thank you very much. Have a great day. Have a great evening, depending on where you are in the world. And we hope to see you soon. Bye.
Thank you. Bye.
Thank you. Bye.